So there are some terms that he would like you to know right off the bat. And the way he's going to format those on tests is that he's going to probably give you questions that are going to tell you when it excludes something, so when it does not apply. So he'll probably ask you questions, for instance, for gelation theory, he'll give you a list of possibilities of when gelation theory does apply, and he's going to ask specifically when it does not apply, or crystallinity. So in the case of metals, he might give you a question where he mentions characteristics of metals, but he wants you to find something that does not apply to metals. So it will be one for polymers. A good example of that would be, for instance, polymers are crystalline throughout. And he's going to ask you in the characteristics of a ceramic when he really wants those of a metal. By chance, can you hear me, guys?
Yeah.
All right, cool. So for biomaterials, so for tacticity, it relates to the substituent groups of polymers. It's a polymer thing, not a metal thing. And for the tacticity types, there's isotactic, atactic, and the third one is syntactic. And it just has to do with the distribution of how those substituent groups are in the chain. If they are like Christmas tree one across the other, or if they are randomly distributed. So for biomaterial, the term for that is basically anything that's biocompatible in the body. Sometimes it has different intended purposes. You want it to be integrable with the body. You want it to be adhesive with the body in the case of bone tissue marrow. Biological material is more or less the same thing, but there's different definitions for that. Last transition temperature is the TG. I believe he mentioned in class the wax, the X-ray wide diffraction, the wide X-ray diffraction, and it's where you get a heat.
No sé.
Say again. He mentioned in class the wide X-ray diffraction, where you get a X-ray and you just shine it through an object and you look at the behavior at that X-ray at different wavelengths. And based on that, you'll be able to determine characteristics of the amorphous phase and the crystalline phase of a polymer. So moving on to step 2, calculating the molecular weight of polyvinyl fluoride triethylene, or in case any polymer. The way those work is he's going to give you, in this instance, a polymer with, let's say, 85,000 repetitions. And so each mer would be one repetition. And this is basically mers linked to each other. So for you to calculate the entire thing, you just take the average weight of one mer, you add it up, and then you just multiply it by the number of repetitions. So for creep, it is just as it is there. It's a time-dependent plastic deformation, and it can occur when something is loaded below the yield point. And it's explained by Suzuki's theory, and you can draw the cloud and with the different electrons, and those electrons displaced due to mechanical stress that is added to the material. And so there are other phenomena, secondary phenomena that would occur in the instance that you have creep deformation. One of them would be necking. If you take, for example, a plastic material or a polymer and you stretch it, then you'll see that at the area where it's stretched, it will be thinned. And so that's called necking because it forms a neck around the material, and crazing. And then you can observe that, for example, you take one of the soda can holder rings and you stretch it, it will form a white area on the area that was stretched. So it becomes from translucent to opaque. That's called crazing. So those two different characteristics describe both the thinning of the material because of the formation of dislocations at the aggregation of dislocations at the grain boundaries, and the change in also the color and properties of the material because of this loading. And fatigue is basically the failure caused by cyclical loading. So if creep is a plastic deformation, then fatigue is the ultimate failure because of it. And most of structures fail because of fatigue failure. But the way it's plotted is on an SN curve. So he probably explained those in class, and it's basically a curve that goes straight down. It looks like this. And if the material reaches cycles to 10 to the 6, then it will be considered to be lasting forever. Otherwise, you'll be able to record the failure point in megapascal or whatever unit you're using at the number of cycles. Any questions so far?
No questions.
No, good.
All right. So for number 4 is Poisson's ratio, stress, strain, and Young's modulus. For those, he's probably going to give you a femoral stent or some other type of material. In the practice exam for the spring, he gave us one of these. So to calculate it, it will be quite easily. One thing you do have to remember is that if he gives you the mass, then you have to convert it to force. And if he gives you the diameter, you have to convert it to the radius. I remember when we were going the review session in class last semester, I made a mistake there and used the radius instead of use diameter instead of the radius. So first you want to get stress. Stress is just the force applied divided by the cross-sectional area of the material before the load is added. And then you divide the load by that cross-sectional area. Then you find strain. Strain is unitless because it's just a length divided by length. So it will be the change in displacement divided by the original length of the material. And then you get the Young's or elastic modulus, which would be just the stress divided by the strain. And Poisson's ratio, it tells you, the one way I like to think about Poisson's ratio is a starburst, for example. Isn't it weird how when you squeeze a starburst on the sides, it expands on the other side? So it's just the way the material reacts to both distance, both horizontally when you put lateral stress and vertically when you put vertical stress. And so that will be how you use that question. Number 5, the way those questions would be added in the test, at least, would be mostly conceptual. I know he likes to ask this question. We got asked this question. And it's just basically talking about the effects in materials, specifically in metals, since that's what we're going over for the first couple chapters. So there's in the crystal lattice, which is the distribution, that is the lowest energy state that a material can form, there's going to be defects. And those defects, they're there, even the most best of materials, but they can benefit the material depending on how they're structured. Point defects can be involved at a single point, and they can be a vacancy, or that vacancy can have either a bigger or a smaller atom than those surrounding it. And the effects of those is the same, although for different reasons. If you look at a smaller atom, they cause something called energy sinks. And so the energy sinks will require more energy to actually overcome it. Instead, when you put a bigger atom, the bigger atoms will push back and resist deformation, which would apply the same concept. More energy to overcome the material, more energy to deform. So when you look at both adding smaller atoms or bigger atoms into material, you would alloy it and strengthen the material. And interstitial atoms, they would weaken the material for reasons we will talk about in packing density later. Then when you talk about defects along a line, they're called line defects. And if you have a small number of line defects, they actually lower the strength of the material. But when you add a lot of line defects, you actually increase the strength of the material. And this is because you're adding dislocations to the material. Think about when a blacksmith, hardens the material by hammering it. That's because he's introducing line defects. And he increases the actual strength of the material by adding stress. And for plane defects, those actually occur at the grain boundaries between two or more separate crystals. So those crystals could be the same crystals, but because of the orientation of those grains have different crystal lattice orientations, then you'll at the section where both meet, you're going to have a defect. And so the aggregation of defects at the grain boundaries is what cause a material to ultimately fail. Any questions so far for that one? I know it was a bit to swallow.
No,
All right. Say again?
I don't have a question. I think you're doing good so far.
All right. So for number 6, I think he assigned this as a homework question. I know he did it for us. So we have to go and calculate this ourselves. Most people, what they settle for is the value online, but he didn't ask this question on the test, but he might for this one this time around. And it's pretty simple. The packing density explains how many atoms are packed within the unit lattice, a unit cell. And it's different for each structure because the unit cell for a face-centered cubic, a body-centered cubic, a hexagonal closed packed, and a simple cubic are different. But the steps to remember is that you're gonna want to remember the radius of each unit cell. And so the way this is calculated is you draw an actual face of the unit cell. So in the case of a simple cubic, you would draw a square, and then you would draw the atoms involved on that face. So if you draw the simple cubic, you're gonna have a square, and you're gonna have 2 quarter circles. And so that's gonna be, and then you're gonna draw the line across from one corner of the square to the other, and that's gonna be the radius, the hypotenuse. And you're gonna want to draw that radius in relation to A, which is the length of one side of the circle, of the square. So you would repeat that for each unit cell, and you would derive these expressions of radius over A right here. Once you get that, you're going to want to determine the VA, which is the amount of volume occupied by the atoms in the unit cell. And so obviously for each unit lattice, for each unit cell, you're going to have different number of atoms. FCC is 4 atoms, BCC is 2 atoms, simple cubic is 1 atom, and HCP is 2 atoms. And so what you want to do is rewrite this expression as the total number of spheres in the unit cell, because each sphere would be represented by 1 atom, and then just rewrite it to include R from the previous equation. So when we look at this in this page, the following one, it'll be like this. For a BCC, it'll be 2V, since we're looking at 2 atoms. And it'll be 2, 4, 3 pi, and then the radius, cubic. So it will simplify it, and you're going to want to divide by the total volume of the space occupied by the unit cell, which would be, in this case, a cubed. In this case, I multiplied by the reciprocal, it will still give the same answer. It would be this expression, and you would just convert this into a decimal form. And so that decimal form represents how much atoms are packed within this system. And so the higher the packing density, it means that I have more atoms and planes packed within the system. Therefore, when I add stress, this material will be able to glide more. And so glide just basically means the probability of material to give in to deformation. So when we think about that, a material with higher packing density would actually be weaker. They will be more ductile, but at the same time, they will be weaker because they are less resistant to deformation. And so when we're talking in terms of strength, it would be the lower packing density material to be stronger. And so for this one, number 7, it kind of relates to statistics. Wait, not statistics, applied mechanics, where we had to take a rod in this case and take the bending moment around it by doing the bending stress. And he'll give you the formula for this, so no need to worry about it. But what you need to remember is that you take the distance of the center of the rod. In this case, it's an I-beam. In this case, it's a rectangular beam, but it could also be an I-beam or an L-beam. And you take the center of that, and you apply the moment of inertia around that center point, and just follow that formula, and it will give you the answer. For number 8, Miller indices. Miller indices, the most important thing is, at least that I struggled with, is just knowing when to identify that it's going to infinity. Because the planes that it actually does touch, I know identify those, but for those that are going to infinity, here's a trick that I remember. If it doesn't actually physically touch the axis, then it's going to infinity. And so the reason why it goes on to infinity is because you're looking at the whole repetition of the crystal lattice within the crystal. So the steps to actually solve this would be, you look at the image, and one trick I know he likes to do is that he likes to, at least he did on our test, he gave us the image of the Miller index, but he gave it to us on the negative plane. So if you do that, you want to take the negative plane and then put it into the positive plane. Or for example, this one. This is in the positive plane, but it'll give it to you on the other side, the negative plane. So take the negative plane and convert it to the positive plane so you can find the correct Miller index. So you see if any of the plane numbers are touching on the axis, and you're going to count that number. If it does not, then you put infinity. The next step will be to take the reciprocal of it, and the reciprocal of infinity would be 0. In the cases where there is no whole number at the end, you're going to want to simplify it and rearrange it so you can get whole numbers. And once you do have whole numbers, you just remember to put the correct notations. There's different notations for planes, a family of planes, or a family of lines, or just one line. Any questions for that one?
Yeah, actually, can you repeat how it would look like if it was like in the negative plane? Because I don't really get that.
Yeah, so just look at, it will be like this. Let's see if I can write on there. It would be just like this image, but he'll draw the negative x-axis, and then he'll give you the positive y and the positive z. That's what he did it to us on last semester. He gave us one where it was like this, but it was in the negative x, and then we had to just push it forward into the positive or extend the plane into the positive, and that would be our Miller index.
Oh, okay, thank you.
Yeah.
But actually, no. But in that case, if it was like in the x negative, couldn't you just put the line on top of the 1 or whatever to say that it was like negative?
Okay, so let's see if I follow. So in that case, you would put a line through the negative. Yeah, but then you would have to convert it, work with negative numbers. So the way he showed us to solve it would be you just convert it to positive. You would extend it into the positive plane. Like you look at the plane and extend it into the positive axis, and then you work with that side.
Okay, thank you.
You're welcome. And so for the Kelvin and Maxwell model derivations, the way those work is, it's just a way to demonstrate. It's a 2-component model, right? A 3-component model to demonstrate creep and stress relaxation for viscoelastic materials. Those mostly occur in polymers, and polymers are a good representation of that because they do form creep. So what you do for the Maxwell model is that you get a damper and a spring in line. And if you can look at this from either a mechanical perspective or an electrical perspective. So from an electrical perspective, this would be a resistor and I believe not sure about this one, about this component, but for the mechanical one, it will be a spring and a damper. Oh yeah, a resistor and a capacitor. There you go. For that will be for the electrical representation. And what you want to do is you put in series, and you set the elastic modulus for the total component equal to the elastic modulus of E1, which is one component, and the second component. Then you take the derivative of that, and the total differential of the elastic modulus, or in this case, strain. Yeah, it would be the differential of the strain would be the sum of both. Then you look at the stress is equal to the strain and the elastic modulus times the elastic modulus, and you repeat this for both components because each one would have its own component of stress and strain. So once you rearrange those, you'll get this equation, which would be the equation for this system. And afterwards, you just need to plug in values to confirm or to reject the validation of creep and stress relaxation. In the instance of the Maxwell model, it will fail the creep test and it will pass the stress relaxation test. So you can look on these graphs. This one will be for stress and this one will be for strain. And because for stress, it shows a constant, that's why we know if it fails creep test.
Alejandro, sigma 1, 2, and 3, they come from different times, correct?
Say again?
Go up a little bit.
Yes, right here.
Yeah, so sigma 1, 2, and 3, no, a little bit higher. I think you had it higher. There, right there. That you have E1 plus E2, and then on top, all of that comes from like different times.
Different times?
Yeah, like where does those sigma come from? The 3 sigmas.
Okay, so the sigma is going to be, since it's in series, the sigma of the entire thing is a sigma for one plus the other. So think about it as you're squishing it, right? So I have this rod, and it's a damper and a spring. If I squish it, I'm adding stress. Then since it's a line, it's the same stress for both components. But if I pull it apart, then it's a stress for each component added.
Okay,
The
thank you.
strain, yeah. So that's where I get those sigmas. And so the takeaway for the Maxwell model is that it's only going to pass a stress relaxation test. So I need to find another model to confirm the creep test. And so that will be the Kelvin model. With the Kelvin model, what we'll do differently is that we'll get a damper and a spring and put them in parallel. So now think about a damper, spring in parallel, and now apply force on it and push it together. So when you add stress, it's going to be the stress of each component individually. That's where we rearrange the sigmas to be the stress of one plus the other. However, when I add strain, since I'm pulling both apart, it'll be the strain of the entire system. So the same principle applies. I would get stress is equal to Young's modulus times strain, and I would find the differential for each one until I get this equation that is in the box by substituting the two components. And in this case, it's going to pass the creep test, but it will fail the stress relaxation test. And we confirm that by setting sigma to a constant and the differential of that to 0. And we substitute it. And that will be our final output. So for the formula sheet, this is the formula sheet he gave us. There were some questions last semester that, for example, this one that had E2G, which is relating stress load to shear stress. He asked us one question on that, but luckily it's just plugging in the numbers. There's also another question on this one, which is Snell's law. Snell's law is basically the angle of light that enters through a material and how much it diffracts. But those were all plug-in values. Any questions you guys might have?
No questions.
All right. Well, that's pretty much the end of it. Thank you guys for coming. By any chance, I do have a question. How's the class different that it's all online?
I mean, I don't know how the class was before.
No, yeah, like I know Christy, he last semester he wasn't good on the transition, so I'm not sure if he like fully got on board now.
Yeah, I mean, we do Zoom and like we spend like a lot of time there, and he like normally passes the time for like 20 minutes, so we have class for 20 minutes more.
All right.
But yeah, he's fully on Zoom and he's doing fine, I think.
The only thing is that like he doesn't have like models, so he can't show us anything, or like he doesn't really know how to draw that well. So
Yeah.
kind of gets
one thing that helped me for the first test is that I drew the unit cells, so I can understand the models, and I also drew the different dislocations, because they'll ask those concepts. But yeah, that's pretty much all we covered today. If you guys have no questions, then what I'll do is I'll post the Bible for biomaterials on the group chat. That'll be a great resource for you guys to go over. And a couple of links that I found were useful in studying. Obviously, this was posted by EMBS. So if you guys would like to learn more about us, you're free to join our group chat. But thank you for coming, guys. I appreciate your time.
Alejandro,
Yes.
will you be available on Monday? Like, do you do this often, or are you available on Monday or something?
I'm trying to do this for the summer, obviously to engage with the students and to also and recruit for our club, but I'll be happy to help.
Oh, okay. And how can we reach you?
Just hit me on group on WhatsApp.
Okay. All right, will do. Thank you.
All right. Thank you, guys.
Bye, Alejandro. Thank you so much.
Take care.
You.